Hello. All right. So thank you. It's very nice to be here the second time. So I will just chop and talk about our recent work that's been published this year on basically noise mitigation and suppression of bosonic errors. I better introduce the different kinds of error inversion that exist in quantum computing to avoid confusion. So the fact that we choose quantum states as resources to do computation means that whatever states we use to encode quantum information, it has to be of a logical error rate of at least 10 to the minus 15 in order to be comparable with classical algorithms. But we know that for now, experimentally, this is still challenging because of the large overheads. But we still have two other options here, and we actually would have to perform these operations in order for error correction to kick in, because otherwise the error threshold will be pretty large. The first procedure that I'm going to talk about is error suppression. So basically, you perform gate operations and then try to drastically or significantly reduce the errors in quantum systems. Um, this is typically not fault tolerant. But there are times where operations cannot be done physically, and I'll show you an example what I mean. And if that's the case, we can still do error mitigation, which is a technique in which now if you assume that all you need is expectation values of observables, then what you can do is you perform the measurement, the quantum state is gone, and you perform classical post-processing in order to reduce the errors that influence the output. So that's error mitigation. So these are the two procedures that I will be focusing on. And so bosonic encodings is actually an alternative to discrete variable encodings for error correction. Basically, I think most of you here know what they are, but I will just briefly mention that these are encodings that are described by the bosonic algebra, and common CV codes are binomial codes, CAT codes, and the famous Goltzman-Kitaev-Presque codes, GKP codes. They can be realized in a multitude of degrees of freedom, not just spatial. You can have temporal, spectral, what have you. And they're also flexible to manipulate and access, including with platforms that include all photonic platforms, light matter interacting platforms, and of course, superconducting platforms. Unfortunately, of course, these codes are plagued with noise. So I will mainly talk about these four common noise channels. These are photon loss, thermal noise, and random displacement noise. What is interesting here is dephasing noise, which is basically random phase distortion. Now, for quite some time, people believe that it is pretty hard to treat dephasing noise because you would need high order, uh, optical devices like a Kerr's effect. But we will show here that linear optics is basically enough, more or less, to treat dephasing noise. So the technique we use to actually reduce or invert thermal noise or displacement noise is using this photon subtraction gadget. Now, mathematics is useless for this talk, so you can understand the map by thinking that it comprises two different processes. Photon subtraction, everybody knows, and either linear attenuation or linear amplification, uh, which we have heard from some of the talks earlier already since Monday. Picture speaks 1,000 words, so I'll just show you the picture of what's going on. So suppose you have a logical state encoded in the cat form. You let it pass through photon loss. Nothing irregular happens. The interference fringes just gets washed out. However, instead of doing that, what you do is first you apply an amplifying photon subtraction gadget, PSG in short, and you see that you can actually fortify interference fringes so large that even after passing through photon loss and then undoing the PSG map with a photon subtraction, with an attenuating PSG, you find that the final state has interference fringes or interference patterns in the Wigner picture almost similar to the input state. And you think that maybe the subject is closed, but unfortunately, no, because the fortification is unphysical, because the Wigner function exceeds 2. There is a workaround for this, and that is using the technique of probabilistic error cancellation. We can do basically error mitigation. Again, mathematics is irrelevant here. All you need to know is that the amplifying PSG that is required for mitigation can be written as a linear combination of something that you can do experimentally. These are basically photon subtraction operations. And depending on the outcome of the photon subtraction, you can actually multiply the appropriate prefactors, which can be negative, which is the reason why this map is unphysical. Unphysical in the sense you cannot implement it deterministically, only probabilistically. And here, this is the graph that shows that in the limit of large number of copies, you can actually perform mitigation below the threshold of not doing anything. This is basically the result. I'm not going to elaborate much. So here you can see that the red, which is the unmitigated case, has much lower fidelities than the blue histograms, which show higher fidelities. And all I want to say is that the theory works for the idling noise, but we also perform numerical simulations and show that it also works for gate noise. Okay, I can elaborate more during the Q&A. Now, dephasing is an interesting one because actually we can perform coherent suppression of dephasing using only linear optical setups like this. So what happens is that you first send an input state through a linear optical unitary, let the output modes get corrupted by IID dephasing noise, followed by an inverted unitary, and you perform vacuum measurements at the end. The result is actually an output state that has dephasing noise coherently suppressed. Now, we showed that in the limit of infinite number of modes, the dephasing channel essentially gets turned into a damping channel. And then we can then invert this damping noise with linear amplification. You may think that, well, infinite modes means zero probability of success for heralding, but it turns out that due to the correlation made by the unitary, even when the number of modes go to infinity, the success rate is non-vanishing. Mathematics again is not important. I just want to show you some expressions to at least motivate the flavor of what's going on. So the output state actually gets turned into a mixture of linearly attenuated states after going through this setup. And in the limit of large number of modes, this is akin to the limit of weak law of large numbers. This mixture gets turned into a pure state, heralded, of course. You may say I'm crazy, it's infinite number of modes. But we also have results, don't worry. We also have results for a finite number of modes, M. And we showed that, at least for the Gaussian dephasing noise analytically, that we can have such an optimized infidelity in the regime of small dephasing rates. And as you can see, actually, the subsequent results will show you, for the case of M equals 2, just a single beam splitter, that the dephasing suppression is already quite significant. Having more ancillary modes over here doesn't really, well, it still improves the fidelity, but not as much as going from M equals 1 to M equals 2. I forgot to mention what VMZ is. It's vacuum-based Mach-Zehnder scheme, because that's essentially what this is. So this is, again, the same graphs that you will see. It's a bit small, and these are the success rates. As you can see, it's pretty high. So we also consider measurement errors, by the way. The details can be found in the paper. So I mentioned linear optical methods, but whenever you read papers on linear optical methods, there's always a plus plus. So what are the plus pluses? The measurements, of course. But for the PSG mitigation, there's something more. Because if you were to implement linear amplification in an experiment, say with quantum seizures, then additionally you would need some resource state. And here we assume that the resource state is perfectly generated, and we account only for the photodetectors, the errors coming from the photodetectors. So this is in some way slightly more nonlinear than we hope for, but for the VMZ suppression, it's mainly linear optical. All we need are the only elements that are nonlinear here are the vacuum measurements. Now, we look at PSG, we looked at VMZ. I forgot to mention also that PSG doesn't touch dephasing noise. VMZ doesn't do anything to thermal noise. Life is never so easy because when you have errors, it's always a mixture of two things or more things. Here we consider a mixture of photon loss and dephasing, or thermal noise and dephasing, same thing, similar thing. There is a theory that tells us that they commute. It's clear to show that they commute. And so we can consider composite noise channels made up of thermal noise and dephasing. And on the other hand, PSG actually also commutes with VMZ in the sense that whether you cascade VMZ in, outside in, followed by PSG, or you do the reverse, it's the same thing. They commute in this sense. So we can actually use PSG and VMZ methods in unison to mitigate. Unfortunately, it's still mitigation, but we are able to then mitigate hybrid or composite noise channels. So I just like to show you the same performance graphs for uh, mitigating thermal dephasing noise and Gaussian displacement dephasing noise. The referee actually, one of the referees actually complained that we didn't consider state preparation errors. So we did it, but obviously we can't do it for all codes because it depends on how we generate or prepare the code space. But we consider the CAT code and we use the very famous setup introduced by this reference to generate CAT states. Now already this setup doesn't generate CAT states accurately. You need large photon number detectors. So this is already introducing state preparation errors, but we also moreover considered lossy detectors over here. And we show that, of course, it's still robust even in the presence of state preparation errors. All right? It's better than doing nothing, is what I'm saying. So this is the summary. We used photon subtraction gadgets to mitigate thermal and displacement noise. And then what is more interesting is that we have linear optical solutions to suppress dephasing noise. We have analytical proofs for idling noise, but we also perform numerics and showed that you can also correct gate noise. And finally, the mitigation and suppression of composite noise is possible with these methods. So thank you for listening.
Thank you very much. Right, time for a couple of questions. Anything from the audience? Okay, here. Okay.
Hello, thank you for the talk. I have two questions. The first one is, so for mitigating dephasing noise, you have this multiple modes and you suppose that the dephasing is IID. Have you considered if you have different noise where dephasing is correlated or anti-correlated? And is it possible to apply it?
Unfortunately, not yet.
Okay, thank you.
Sorry for that.
Thanks. And the second one is, what is the minimal number of modes for applying those schemes?
The minimum number of modes
Yes.
for applying those.
Like, in particular, the dephasing mitigation scheme.
So here we consider. So the behavior is actually different for whether you have, depending on whether you have an infinite M or a finite M. So for an infinite M, if you look at this expression, so for the infinite M case, you can actually really completely convert the IID dephasing noise, at least, to something that looks like a mixture of damping channels. For finite M, we showed that M equals 2 is sufficient to have significant suppression of dephasing, but it's not exactly going to the mixture of damping noise effect. So you need more. So it maybe you don't even need infinite number of ancillary modes. Just sufficiently many would be enough.
Okay, great. Thank you very much.
Next question is.
Yeah, I wanted to ask, mostly in the case of the photon subtraction gadget, because it's a probabilistic scheme, right? Like when you fail, which I guess in the photon subtraction you fail more than you fail in this case.
Correct.
what do you do? Like you keep the state, you have to drop it, and
So here we discard the state. We just do the simplistic way of heralding. Yeah. So basically, we only keep the successful heralded measurements.
and like what's the usual success
The
probability?
success probability, because it's 10 minutes, so these are the numbers.
Okay.
So you can find the same set of numbers in the paper, but take these numbers with just a pinch of salt, because this is the best case success rate. And we know that already from the latest papers by Tim Ralph, when you are doing it with quantum seizures, the success rate actually drops exponentially with the average photon number. So this is the success rate in the limit of small photon number regimes. So, but still, it's not 10 to the minus 3 or 4. So it's hopeful, I say.
Thank you.
But do I completely like the idea of error mitigation? Maybe not. So we are still looking at how we can actually suppress photon loss instead of just mitigating.
Okay, wonderful. Thank you very much. Let's thank our speaker, both Yong Siah and the rest of the speakers for the session.